It says that a constant net force of 75 newtons acts on an object initially that is at rest, and it moves it through a parallel distance of 0.6 meters. So let's write that down. So we have an object, doesn't matter what it is, and there is a force applied of 75 newtons. What is the unit for force? Newtons. So we're good there, no conversions. All right. And then it says that it is displaced parallel, which means in the same direction. And what is that displacement? It says 0.6 meters. And so we could say x is equal to 0.6 meters. Now what is length always measured in? Meters. So we don't need to do any conversions there. And now the question. Oh, and it said that the initial velocity was 0 because it was at rest, right? And then it doesn't tell us what the final velocity is. We may be asked that, all right? So let's continue to read. It says, what is the final kinetic energy of the object? I don't know. We got to figure that out. And then part B for that is, so let's figure that out. So part A of the question wants to know what's the final kinetic energy. Part B says if the object has a mass of 0.2 kilograms, so we're going to say 0.2 kilograms. What's the unit for mass? Kilograms. So remember that's the mass. Mass equals 0.2 kilograms, so it's kilograms, right? If it has a mass of 0.2 kilograms, what's its final speed or final velocity? Right? And we don't know what that is. And I just kind of assumed we'd have to figure that out.
Can't we not use 0.2 for the first part though? Because that's only for part B.
I'm sorry, what was your question?
So it says that if the object has a mass of 0.20 kilograms, it doesn't say it does for the first part, it only says that for the second part. So we have to figure it out for the first part.
Yeah, we have to, it's not the specific question. Her question is don't we have to figure out some other stuff too? Kind of, I'm generalizing. And the answer is yes. To answer these specific questions, we're going to have to go back and figure out certain things, right? And so let's do that. To find the kinetic energy, there's a bunch of formulas that we could use. So here's so there's some issues here. So the formula for kinetic energy is 1/2 times the mass times the velocity squared, right? And if I have an initial kinetic energy, I would do that. And then the final kinetic energy, I would do that. Here's the problem. I know the mass, but I don't know the final velocity. And I think that's what she's like asking the question about. She's like, well,
We don't know the mass.
Well, yeah, we can't assume that it's 0.2, but if it's 0.2 at the end, it'll be 0.2 at the beginning, all right? So we could use that. But that's not really going to help us either because we still don't know what the final velocity is. So I can't necessarily figure out what the final kinetic energy is because I don't know the velocity. So then we got to backtrack. Well, how can I find the velocity? Well, what do we know? We know the force, and we know the displacement, and we know the initial velocity. Oh, hey, I do know this. The initial kinetic energy, if this thing's at rest, what's the initial kinetic energy? 0. All right, maybe we could use that. Huh. So we got to think of a formula that relates kinetic energy. I know one. Didn't we say that work is the force applied to an object over a distance? Yeah. And didn't we also say at one point in time that work could also be the difference in kinetic energy, which is really the final energy minus the initial energy? Yeah. So we have a force, we have a distance, I could calculate the work, and then I could set it to this and maybe solve for the final kinetic energy. That makes sense? Okay, so this is going to be hard. We got to put on our thinking caps to keep track. First, let's figure out what the work is. Well, the force is 75 newtons times the displacement, which is 0.6. Okay, so I'm going to run out of some room here. So if I come over here, then my work is equal to 75 newtons times 0.6 meters. And so if I plug that in my calculator, 75 times 0.6, we get 45. Good. So my work is 45 joules. I know that it's joules because I had Newton meters, and that's what joules are. Okay, well that's good. Now we said that work is equal to delta K, and delta K is equal to the final kinetic energy minus the initial kinetic energy. Cool. Well, we said that that is equal to 45 joules, which is equal to the final kinetic energy minus, what was the initial kinetic energy? 0. So 45 joules is equal to the final kinetic energy, isn't it? Let me check my notes. Hey, that's what it is. That's the final kinetic energy. Cool. So that worked out. So we're going to come back up here. Part A, 45 joules, final kinetic energy. Now I would guess that we could plug that into this formula and get our final velocity. In other words, I could say that my final kinetic energy, which is 45 joules, well, let me start down here so it doesn't get a little crazy. So I'm going to say that my final kinetic energy is equal to 1/2 times the mass times the final velocity squared. Okay, that's cool. Or 45 joules is equal to 1/2, and I'm not going to write the units in there for now. We'll do it later. Is equal to 1/2 times the mass. Textbook says the mass is 0.2 kilograms. And I don't know why I plugged in the 0.6. Probably because my notes are way over there by my podium. But anyways, I end up with 450 is equal to the velocity squared. So now what do?
Square root.
Take the square root of both sides. What is that, about 21? Well, let's just plug it in the calculator and see. 450 raised to the 1/2. You know, that's another way to take the square root, right? Seriously, boom. 21.21, or well, bam with the bacon sizzle.
Oh, you're so cool.
I am.
You should be a rapper.
21, it's about 21. Okay? So we could say about 21. What's the unit for velocity?
Meters per second.
Meters per second. Now let me double check my notes. I think that's right.